Okay, today I'm going to be talking a little bit about the project that I've been working on the last year. It's progressing year by year, and I'm adding more functionality, and I'm doing more things over time. Last year I had remote control working with preamps, but I didn't have a web server involved. This year I involved a web server as an additional way of getting in, so I'm going to talk about that. Don't have a live demo for the talk today, but if you see my table in the Pass Lab room, I can give a live demo and show these things actually running. And if people wanted to, you can pass that around. That's the demo box that I've been using for development, and I've got a few more of those over at my table. So let's get into the lecture. So what I'm going to talk about today, a little bit about the project history, then the specific product itself, project, which I've got spare boards for, and the source code will be posted fairly soon. Use that for my R&D testing. And then I'm going to talk about how it actually works, how the communication goes between humans and the web server and the manageable boxes, preamps, SPDIF switches, HDMI switches, and so on. But concentrating primarily about these kinds of messages, the RF messages and the web control URLs. Hopefully it will make a little bit more sense once I get into it. Okay, so.
Can you tell us the exact function of what we're looking at?
Okay, right. So that preamp is basically using a Burr Brown PGA 2311 chip. It's analog in, analog out, unbalanced. It comes in a dual 5-volt version and a dual 15-volt version, and basically it gives you volume control from minus 95 dB up to plus 32 dB in half dB steps. Very good specs, 120 dB, signal to noise, all the usual kinds of good specs. And it turned out to be fairly simple to interface with as long as you follow a few rules. Some op-amp pre and post buffering, circuit board layout techniques. I can go into that in more detail after the talk, but that's basically what that is. That is a
preamp that's remote controlled.
Yes, a remote controlled preamp. Line in, multiple line out, multiple line in, one line out, and a headphone out. Has a headphone preamp, headphone chip as well. The TI TPA 6120. Very, very nice chip.
One or two.
Sorry?
One or two watts.
Don't know what the output power is. More than enough for headphones though. That one can also run as high as dual 15 volts if you need to. Okay, so a little bit about the project history. I started maybe 7 or 8 years ago working with AMB Labs. We wanted to come up with a DIY approach towards remote control of things. Preamps, amps, switches. Basically, I gotten into the hobby by building kits. Kits from eBay, kits from other sources, and most of the time the firmware was not extensible. You couldn't improve it, you couldn't change it. You were stuck with what they gave you. It was interesting, but I wanted a lot more. I wanted to be able to customize things, and I wanted people to be able to download the code and be able to customize it themselves. So I worked with AMB on our first project. It was the Alpha 10 preamp. You can see an example of it on his table. He's here with it. And that was a relay-based R2R attenuator. It was fairly well received, and that ran in the hobby for, I don't know, 4 or 5 years before I sort of got more interested in the solid-state volume controls. The relay volume controls are interesting, a little bit large to build, a little expensive, a little bit noisy. When you turn the knob, the relays go up and down. So I wanted to get into solid-state volume controls. So let's see, that's pretty much enough for that slide. Just some of the background history. One of the things that I did after designing the Alpha 10 with AMB was go from an infrared handheld remote control to something that was a little bit more fun to use. A volume control that has an OLED display. It's got a minimum amount of buttons. Right there it's sitting in a charging cradle, so it has rechargeable batteries and Qi charging. And the key change that occurred during those years was I moved from using infrared to RF remote controls. Infrared remote controls, as you know, you point your remote at your stereo and it sends only. It can't receive. It can't receive updates. So if you change the volume and you walk over and you change the volume, if your remote control had a display, it wouldn't stay in sync. It wouldn't show the current. Having a bidirectional communication actually made a lot of sense, and so I moved away from the infrared remote controls to RF. Some of the things that I added beyond just volume controls, I took an SPDIF switch and I added the remote control infrastructure to it. And let's see, I don't know if you can see the picture or not. There is an XB in here somewhere. I think it's underneath here. The XB is basically an RF module, a 2.4 gigahertz module that lets you have a serial session between two endpoints. If you send 9600 baud in one end, it goes through the radio link and you get 9600 baud TTL at the other end. Very, very simple. It's 5 volt based, it has 4 wires, 5 volt ground, transmit, receive. It can't get much simpler than that. So I started buying more and more of these XB radios and adding them to various projects, and this was one of them. The SPDIF switch, I have an HDMI switch, power line switching, later on maybe some speaker switching, but the key was using RF. And with this RF technology, it forms essentially a party line, a multicast, so that when any of these units send something, all the other units that are tuned to the same frequency receive that message. And that can actually be beneficial. If you turn the volume up on something, you're sending a request to get the volume, you're getting the volume coming back. In that reply, any other listener that's tuned onto that network can now learn what that volume was, and he didn't have to transmit anything. He can receive stuff for free and power on after things have already been set, and the minute somebody hits a volume control, there's a request, a response, everyone hears it, now everyone's updated. So after the relay project, I wanted to get into the solid state volume control, and the PGA chip was a very common one. A lot of people were experimenting with it. PGA 2310, 2311, so there's some more chips in that series. It's a 16-pin chip. It's simple to interface, and it has analog in and analog out. And there's a lot of people that were trying to build these, and they had various difficulties. There was some difficulty in getting the firmware to work well, getting the chip to boot properly and not fry itself. So after a couple of years of trial and error and learning and doing a lot of reading, came up with a prototype circuit, and that's what the preamp is that's going around. It's using this new circuit. So what did I do first? Well, I didn't want to start totally from scratch. There are some of these boards that you can buy, a very common board that's like a $30 board on eBay, and that's what you get from China. This is the basic engine here. It's got a couple of relays for inputs, power supply on board, and there's the surface mount PGA 2311 or 2310 chip right there. So I bought the kit. I bought the engine itself, and it came with an LCD controller and a remote control for infrared, small little credit card remote, LCD display, and a rotary encoder. And it's like, okay, this is a good platform that I can use to study with. Played with it for a bit, really didn't like the LCD display as much, didn't like that it was kind of slow. If you turn the knob too fast, it would skip events, it would drop events. The remote control sometimes would lose things. You would send an up or a down, and it would get confused, it would go the wrong direction. It was buggy, and again, most of the things that are coming from eBay China is closed source. You can't change it, you can't improve it, you can't modify anything. So first step was keep the engine itself and replace the controller with my own. So you can see I tapped into the cable here. It was originally going to an LCD display. Here I'm going to my own Arduino Nano controller, and then there's an LED display in back of that. And see, there's my XB and an optical rotary encoder. So I changed quite a lot. I changed the fact that it's now using RF remote control. It's using an optically sensed rotary encoder, much higher resolution, 360 pulses per revolution. So you can turn it and actually get an awful lot of data coming out of it, as opposed to the mechanical rotary encoders that come with these kits. I think they're 12 or maybe 24 pulses per revolution. Very bouncy, very mechanical, not a really good feel at all. So I played with this for a bit and spent most of the time on the software to control it. And then I met somebody online through DIY Audio, and we ended up working together to design a custom board. And that's what's in the unit going around. So thank you to Jeff Wilhelm. He's a friend of mine. Never actually met him, but we've been working online and emailing several times a day. He likes doing PC board layout. He's got a good handle on analog design, and he wanted to work on this project, but he's not really a software guy. I'm almost the opposite. I'm a software guy, not as much of a hardware guy. It was a good partnership. So the two of us got together, and in a matter of a few months, we had the first board out, and that's basically what's in that box. We used a small 4-inch 2-layer board. We wanted to have board-mounted RCA jacks, minimize wiring, a couple of analog inputs, a couple of analog outputs, and being a headphone person, I wanted to have a pretty decent headphone chip as well, so we used the TPA 6120. Another big change was this LED display. Can't really, well, I might be able to demo it later on here, but you can definitely see it at the table. It's big and it's bright. You can see it from across the room. My vision isn't the best. I can see it from the other end of the room. With an LCD display, the fonts are kind of small. You really can't read them. This is big, it's bright, it moves very, very quickly, it's dimmable, you can get them in different colors, you can get them in alphanumeric as well as pure numeric. So it seems to be a winner. You can stack them next to each other, you can get 8 digits, you can spell things out because it is alphanumeric. And then for RF remote control, reading some of the maker forums and online groups, people were using Bluetooth modules, this thing called an HC05, and similar to the XB, you have a pair of these Bluetooth modules, you give them the same pairing code, and every time they power on, they'll just instantly pair with each other. And like the XB, you send 9600 in on one end, TTL, you get 9600 at the other end, and it forms the radio link. So you can use whichever one you want. You can use the XBs, which tend to be about $20 a piece. They're a little bit expensive. Or you can use a pair of the Bluetooth modules. The code doesn't change at all. That's kind of the cool part. I'm speaking just regular, simple, readable, human-readable ASCII over the air, and the fact that the data is being carried by XB, which is a form of Zigbee, or Bluetooth HC05, doesn't matter to the code at all. It's sending a string, the other end is getting a string, it's parsing it, it's sending the response back. So you have the independence to choose those or possibly other RF modules, even wired. You can run pins 2, 3, and 5, so to speak, across from one box to another. I just thought it was nicer to have a wireless command infrastructure. You need wires mostly for your audio path, but for control, you're not sending bulk data. You're not sending the audio over RF. You're just sending commands. Change volume, change input. What is your input? Change brightness. These are small little commands. They can easily work at 9600 baud, and not having to run a separate wire for your remote control infrastructure, that was kind of nice. Another benefit of the RF is that you can put things behind doors. So if you have a living room, you want to close your doors, the RF will go through that. You don't have to look at your equipment. And another benefit is that you can actually have the web server downstairs or in the basement, somewhere hidden away if you have a noisy PC, and the RF will go through your house. So there's an awful lot of benefits to the RF remote control. So this is what the board looks like. And I'm not going to talk too much about the board. I can answer whatever you want about the board. We can go into the details later on. I do have some board blanks with me. This was the first rev of the board. I picked blue for a revision. I had a blue board, then I had a green board with some improvements. Now I have a white board just to separate them all out. Probably have one more spin of the board and then do a group by. Basically just what's going on here. We have some op amps for pre and post buffering. This chip right here is the PGA chip. It is available in surface mount, but I like the ability to put it into a dip because you can configure this board to be dual 5 volts or dual 12 volts. I'm not sure if all of the chips are available in both voltages with surface mount, but they definitely are in dip. Plus, early on, I was worried about frying this chip. If you go online and you read about people using the PGA chip, there is a little bit of magic in how you power sequence them, how you boot them up, and if things don't quite go right, the chip goes into what's known as SCR lockup or latch up, and it just goes into thermal runaway. Not a good thing. Didn't really want to have a soldered on chip in case I did make some mistakes or I wasn't able to properly talk to this chip and power it up and down properly. So far, I haven't had any fried chips, so that's good news. You could actually solder it down. But initially, I did put it in socket. Let's see, on this board, the TPA chip is right here, so that's the headphone chip, and then the headphone out would come through here. Input relays for the ports and output relays as well. So we have a couple of input ports, one output port here, and then an output port for the front headphones. Power supply needs were very simple. I'm just using a linear 7805, 7905. You could use something fancier as well, but this actually gives you low enough noise and it powers the digital section which needs 5 volts and the analog section which needs plus and minus 5 volts. Let's see what else. We have front ports for the rotary encoder, for programming, for the LED display. And that's about it for this board. It's fairly simple, nothing really adventurous. Standard op amps, fed op amp on the input, bipolar op amp on the output. I believe it's an OPA 2132 input and NE 5532 or 34 for the output. And it puts the PGA chip right in the middle. Over here is the Arduino chip, so that's the controller, the brains for the entire system, and that's running a standard Atmega 328, the classic Arduino chip. Okay, so just another shot of the box, what it looks like. 3 inputs on the rear, 1 hidden input as a header meant to be used like for an internal DAC board, a line out here, and then you have a headphone out up front as well. Version 2 of the board, I went to green, and I wanted to move things around, make it a little bit easier to use, a little bit easier to build. We removed most of the surface mount that was on the bottom of the board, so it's a little bit more buildable in terms of a reflow oven. And I changed the serial port to fit the exact footprint of this Bluetooth HC05 module. So it plugs directly in. Notice that this is the whole module, and the antenna you can't see, but it's a PC board trace antenna that would be up here. Now, in a plastic box, this works completely fine. In a metal box, it would be blocked. So what I would probably do is remote this to be outside the box. This is simple, plus 5 volts, ground, transmit, receive. It's 4 wires. I could conceive of maybe an RJ11 or RJ12 or something that would be on the back. The cable would go to the connector, you run a long phone cord, and then you can mount this in a small box. It's essentially like an antenna. So if you get it up high, you'll get better coverage. It can be remoted or it can be put inside the box, your choice. Oh, and the other thing that I added with this revision was LEDs to show which port is currently active. So when you switch inputs or outputs, the LEDs will go on and off. This isn't the neatest build because I used an old rear panel from the previous spacing, and I was only able to fit 2 of these dual RCA jacks that are stacked in there. The LEDs, the idea is that they would go to the rear panel, and when you're looking at the wiring side, if you're trying to debug something, well, you might have a couple of inputs plugged in, but which is the currently selected one? Ah, okay, that is the currently selected input, and that's the currently selected output. If I had the headphones active at the time and I turned off the line out, this would be out. Well, yeah, my amp is not going to be getting any signal, and I'll know that, and I'm not going to worry because I'll see the LED state. So just a minor feature improvement for this one. Okay, so that's pretty much all I wanted to talk about on the hardware platform. The really cool thing, and I think what's new, is the strategy of how things are going to talk over the network. And this strategy kind of evolved over time. I didn't really come up with it at once, but just developed it a piece at a time. First part, let's talk about the green side. So the green side are your equipment, your boxes. The preamp, such as the one that we're passing around, an HDMI switch. I didn't really do an entire HDMI switch. I took an off-the-shelf HDMI switch that was infrared controlled, and I took an Arduino, learned the infrared codes, used a back-to-back set of transmitter receivers, you know, real hacky, and now I have an RF interface to the HDMI switch. I did not have to do the complicated HDMI board layout. I didn't have to source the parts, didn't have to worry about the timing details. I just considered the board to be a unit in itself. It was remotely controllable over IR, and I just created a little bridge that would go RF to IR. Plus, I can add some value. We can name the ports. We can save the port state in EEPROM so that when you power it down, power it back up, it'll remember the last state. You can have it automatically scan. So it's kind of a central theme to be able to take non-manageable things or minimally manageable things, add some fancy management to it just by gluing on this infrastructure. And now we've got a value add. We've got something that does a lot more than the vendor initially planned. And it's just a loose coupling with either IR or serial or something like that. Same kind of thing with the SPDIF switch. I took an example Wolfson, I forget the chip I used, but a Wolfson SPDIF transmitter receiver that can accept optical or coax, and I just grafted on an XB and an interface with some relays to select the inputs. I have an RF remote control, a handheld remote. That was what I showed a couple of slides back. That guy right there. So he is also speaking the same network. This is, think of this as one big party line. Anybody who talks here, they all receive. And basically, if somebody does a volume control change here, it goes into the network, and they all can use it. If there's a web server here, somebody does a volume change here, the web server doesn't have to actually transmit, doesn't have to ask. If somebody asks a question and you hear an answer and you overhear that answer, you didn't have to become active in that conversation, but you now gleaned a bit of management information. So that's kind of a recurring theme in using this broadcast, party line, multicast kind of network. Note that you don't get that with the Bluetooth modules. Bluetooth currently doesn't have a mesh kind of design. Bluetooth is a pairing of two modules. So if you go with the low-cost Bluetooth modules, you're not going to really have this kind of shared network. You're going to have a point-to-point connection from one endpoint to another endpoint, and that would be it. That would be it. It's really small scale, it's less functionality, but it's an option, and if you didn't have a lot of things that you wanted to manage, and if you only had one sender and one receiver, it'll work fine. And one of the advantages of Bluetooth is that if we install the HC05 Bluetooth in one of these things, your phone, your PC, your laptop, anything that speaks Bluetooth Classic, not low energy, but Bluetooth Classic, would be able to connect to this thing and talk to it. So it's an option. I personally prefer the XBs because they're much more functional, but they're higher cost, they're more fiddly, and it's really the cost issue. $20 a radio is kind of expensive. So this is your equipment network, and think of it as person-to-box communication. Over here on the beige side, you've got your home network, your Ethernet switch, your Wi-Fi router, not necessarily the public WAN. We certainly really don't want your volume control and things to be reachable over the public net. Certainly could be, but when I say network, it's really your home LAN. There's not even a public connection here. You can use your phone, you can use your browser, anything that can get to a website. And for the website, we're running a small box. I just have a laptop. You can use Raspberry Pis, they're very common. You can use Arduinos. You can use a new chip from China, the ESP8266. That's a $10 chip that has an embedded web server in it. It can run Python code and Lua code and C code, and that's another alternative. I'm using a standard Linux Intel box here, and this is the communication that I'm going to be talking about. I'm going to talk a little bit about what this link looks like and a little bit about what this looks like. So the user is going to be sitting at a browser. He's going to want to be able to change something over here. He's going to type something into the browser. It's going to connect over Ethernet or Wi-Fi to your Linux box. It's going to run this little web server. It's going to respond to your URLs. That's going to it's going to encode a message over RF, go into the network, talk to your box. The box is going to respond back. The web server is going to get the response, formulate it back to the user, and he's going to get the reply. So that's the idea. You can do IP interface to things, you can go direct RF interface to things, and you can even go infrared as well. One box that I didn't show is an infrared to an infrared gateway that converts infrared to RF. Then once you're in RF, you can speak to the rest of the boxes. If anybody has any questions, feel free to just interrupt me. Okay, so what does it actually look like? And I'm not really suggesting that this protocol is the final one or that it's super advanced or that it's even all that intelligent, but it does work, it's simple. My current belief is start really simple, get something to work, prove it, play with it for a bit, see if it's growable, see if it's going to be reliable and robust, and then go more advanced over that over time. Rather than starting very complicated and then trying to get everything to work all at once, do it kind of a step at a time. So what's actually going on here? Well, I took a lesson from GPS modules. GPS modules send out a message once a second, and they send out basically the current time of day. They can send out the latitude and longitude and things. But they kind of had a really neat short message type. And the message type has these fields in them. Starts with a $sign, you get the command, you have values, and then you have the closing of the message, an asterisk as a flag, and then 2 characters of checksum. The checksum is important because with both of these technologies, with Bluetooth and with XBee, you can get data corruption. You could maybe be too far away. Maybe there's some jamming. It is 2.4 gigahertz, so it could have some interference. So you need a checksum. You need a way to say, yeah, I got a message, and it looks like it's a valid message, but does everything add up? And so the checksum basically takes all the characters, applies an exclusive OR, standard kind of CRC checksum, and then puts the output in 2 characters of hexadecimal ASCII. It's exactly what GPS uses. And GPS has been using this for decades, and it works, it's simple. There's example source code on how to encode and decode the checksums. And so, okay, why not? Why not use something similar to it? So let's go through the example here. A $sign to introduce it. I just arbitrarily chose 2 characters. Maybe I'll choose more characters, maybe I'll choose less. But I wanted to keep the message sizes really small. You could go really verbose and spell that out, volume, control, change it to 39 dB. But remember that if you're holding a key and you're auto-repeating, these messages are going to go back and forth between you and the object itself, the thing that you're managing. So keeping the message size very small mattered. Also, there's a limited packet size. You want to keep the entire payload so it fits within a very small RF transmitter. And the XBees and the Bluetooth modules both really prefer small packets, so we keep it small. So I'm sending a query across here. The left side is the master, the right side is the slave. And I just chose a question mark as a marker for a query. What is the volume control? The star2A is just the checksum, but the message part is really just VC question mark. What is it? It responds back. Okay, you asked about VC, so I'm telling you what the VC is, volume control. The question mark is the question, the equals is the reply, and then here's the value in plain English. It's just plain old ASCII, 39 dB, and then the checksum. AI, let's see, I need to be able to choose the analog input. How about AI? Fine, it works. What is the analog input? Okay, I'm on port number 0. Analog output, I'm on port number 0. That's a little bit hard to see. Well, you can see it below here. KS, a knob step. How much do you turn the knob before it registers? Does it move very fast or does it move very slow? So you can control that. What is the knob? What is the knob step? I set it to be 4. BR, brightness. I want to be able to change the LCD or the LED brightness. What is it? It comes back with a code 0 to 9 for the brightness. So that's the general idea. A request, a response, response. And you can think of it as a dictionary. You can add more commands to the dictionary. You implement it on both sides. You write the code on the source side. You write the code on the managed object side. Yes?
Can you stack commands?
Say it again? Like with a semicolon or something like that? No, I decided not to. I decided that each one, I want them to be atomic, discrete, and connectionless. Let's talk about if we stack them. If you stack them and you said do two things at once, suppose one of them failed. What do I do? In some protocols, you either do both of them or you do nothing. And if you do both of them, you start doing one, the second one fails. Usually you have to do an undo. It gets complicated. You can chain these back to back. You send in one request, you get a response, you send in the next one. If there's a need later on to piggyback them together, we could. But the danger is you're going to start growing your packet size, and you have to parse these out, and there's more rooms for error. So yeah, I intentionally decided it's a request and then a response, and then you're ready to take the next request. Yes?
What's the latency like for this?
It's quick enough so that you can turn the knob very quickly on the remote, on the unit itself, and you'll see the update on the display pretty much real time. Yeah, it's fully synchronous. It's fully synchronous. So a send and a receive. And in fact, I'm not using sequence numbers or acknowledgements yet because I haven't needed it. If you find that you are having difficulty receiving the packet, you send it twice. So if I send volume control changes twice, go to 39, go to 39. The second one is not going to hurt. If you get both of them, if you get just one of them, at least one will work. It's not an incremental. It's not like add one to it. That wouldn't be, what is the word, idempotent. That wouldn't really, it would add, you know. So this one, you can overlay them on top of each other. And so far I have been using a transmit twice kind of paradigm, and it works. One request in, twice as an answer, just to make sure that the source guy gets it. Any other questions? Okay. So that's the RF side. It's fairly simple. It's lightweight. It could be made more efficient. It could be converted into binary. You could probably have 1 or 2 bytes instead of all of those strings. But I wanted to be able to run a terminal program, a mini-term or hyperterm or something, and see the exchange going back and forth. See if I'm dropping characters. See if I'm sending out the wrong string. See if something's wrong. Because I'm developing this code at the same time, it's nice to have a little protocol scope where you can see the exchanges going back and forth. So because this is more DIY oriented, it's not really closed source, it's not production based yet. I wanted people to be able to understand it, see it, change it, modify it, understand it. So I kept things very simple. And even though it's very simple, it's still efficient enough and it does get the job done. So all of that was on the RF side, from the web server to the preamp or from the remote control to the preamp. Now how do things work from the person to the web server so that you can get IP, TCP IP access to your boxes? So one thing that's very common these days in remote management is called REST. To be honest, I don't even remember what REST stands for, but it is an acronym, and it basically implies that you've got URLs of this form, just like you would go to a website, but you structure your commands and your responses in simple, ASCII, easy to formulate, easy to read hierarchy with slashes. So for example, if I wanted to get a value, I just create a verb, get vol, and I just type this in. That would be the address of the web server. The request goes to the web server, it parses the get vol, and it figures out, okay, what kind of RF transmission do I need? Well, a get vol is the VC question mark. So we would have a VC question mark going to the preamp. The preamp will respond back, here is your value. The web server will take that value and then map it back into what's called JSON format, JavaScript object notation. That one I do remember. And that's just a bunch of brackets and curly braces. You'll see some examples later, but it's very readable. It's very human readable. Again, it's not binary, it's simple. You can look at it and you can say, okay, I didn't do something right, I need to change my code, or this just doesn't look like it's within the right range. If it's all binary, it's a lot harder to deal with. So, what does it look like? Well, it's a little bit hard to read on this board. I will be putting these slides online. I'll provide a link to a DIY audio thread so you can download the slides.
I looked up REST.
Sorry?
REST, representational state transfer.
There you go, there you go. Somebody's got a phone, okay. The whole idea is that it's stateless. You send an entire command in that fully describes everything you need to do, and the web server will process it, action it, and then send a simple response back. It's very synchronous. There are REST services that require you to log in or authenticate first, but because this was in a captive network, it's on your private network, I didn't really see the need to complicate things by having to log in, log out, time out unused connections, things like that. So it's just a request and response. So I've broken the screens into two sections. This is what's happening on the web server, and it's sending out the serial I/O over RF, and this is what the user is going to see and type in. So if the user did a request, and you could either type that URL into your browser, or because I'm a command line guy, there's a Linux command called curl which fetches a URL. It basically does a remote fetch or a get of this address. So you could put that on your laptop, you can put it onto anything that's speaking IP, give it a port number. This is some Python code that I can explain later on if people want to. But you type your commands in, it sends it across, and I have a compound command here that when the user types in get all, it knows to talk to everything in your network. Talk to the SPDIF switch, talk to the HDMI, get everything that's manageable from all of them. Currently, I don't have a lot implemented because this is just being written as I'm talking. It's just written last week, basically. But it displays various things here. Get me everything. It shows the get vol request and the response, 39 dB. Get me the current analog input, it's on port 1. Get me the output, it's on port 1. Get the knob step. How fast can you turn the knob before it registers? It's a coded value currently, 0 to 9. Get brightness. With this, basically, you can see that you can pull across the entire configuration of the box and save it locally. If you had to upgrade your box, if you broke your box and you wanted to transfer the entire configuration over to a new box, it's a dump and restore operation. You can pull down everything about your box or your entire network, and then you could feed it back in again. If you wanted to copy it to a new box, you end up doing a set all, or you do a bunch of discrete sets to push all these values back over. So that basically, I'll do a get all just to remind myself what the dictionary is. What are the various commands? Is it get volume? Is it get V? Oh, okay, I wrote it as get vol, so that's what I have to type in. Some more details. Okay, so this should be a little bit more readable. And this shows a data stream going across. I'm starting a web server here. It's a Python server sitting on a certain port, a high port number. And for debug, I'm just displaying the stream back and forth. But when I did the get all, it's asking for volume control, it's getting the value, it's asking for the input, it's getting the value, analog output, value, knob step, value, brightness, value. Finally, after it talked to everything that it needed to, it prints a log entry, typical Apache style log entry saying, okay, I processed everything, now I return a response back to the user. And the user would end up, there we go, it's a little bit easier to see there. It formats it in JSON format. So JSON is, the brackets are a way of grouping things together. The curly brackets are a way of having key and value. So get vol is the key, the value is okay, status. So the command and its status. Another key value pair is value and 39. I was asking about volume, here's the value, and it's minus 39. I could add more tags to this. I could say units decibels or units human if we went from 0 to 99 for volume control. So this is the general idea. Without getting too much detail about what JSON is, that's what it looks like. It's simple, it's small, it's lightweight, it's very trendy. A lot of web services are now using JSON format, and I'm using it now as well. So if I wanted to do some discrete gets, I'm doing one thing at a time here. I do a big fetch just because it's a compound and I wanted to remind myself what the verbs were, and the I/O goes back and forth over here, but I wanted to get the current volume level. And you could go over, turn the volume knob, and then type in this command, and it'll always show you the current value because it queries it right when you do the command. You type the command in, sends the XB request over, gets a response back, formats in ASCII. So I did a request for get volume, I did a request for get the analog input, get the analog output relay status, a knob step, just a numeric value from 0 to 9 of how many of the revolutions do we skip before we actually register a turn. It's a rotary encoder, it's not a pot, so it's essentially sending out pulses. Normally it would send 360 pulses per revolution. That's a lot of changes. If you turn it at that rate, a quarter of a turn would give you 95 dB of range. That's insane. So to make it more usable, I drop every N step, every second step, every 8th step, every 24th step. And that way you can basically turn the knob as slow as you want or as fast as you want and get the kind of feel that you want. So that's the whole idea on the get knob step. And then brightness, the LED display brightness. So this is how we're doing gets. A get is a read. You're fetching the current value. And just another view of what the gets look like. Another view on the server side of what it looks like. And then sets. Well, reading is one way of doing things, but you want to be able to modify things as well. Frequently, you'll do a get first, get the value, make a decision, and then say, well, his volume level is at this point, I want to change it, or it's pretty good, I'm not going to change it. So a lot of times you'll do a get and then a set, but for the set format, it's very similar, but you set the value as the trailing number after the slash. So we had a get knob step, we have a set knob step, a set brightness, a get brightness, set knob step, set volume, get volume. So it's simple. It's just really, really simple. You could type that in, you could script it, you could automate it. And basically you can model everything in terms of gets and sets, reads and writes. Everything is modeled as a variable. You're writing a 39 to the volume control register, it becomes 39 dB. You write a 1 to the input port, relay 1 clicks down. You do a get of which current input, it looks at it and it says, okay, relay 2 is clicked down, you get a 2. That's really it. That's the management in a nutshell. Gets and sets using these web-like URLs, having the RF stuff happen on the background. So you type in a command, a flurry of RF stuff goes back and forth. It gets all the data it needs. It summarizes it, processes whatever it needs to do with the web server, and then returns back to the user one of these bracket or curly brace kind of JSON strings, which then would normally be received by a process. It would be received by some automation or a script. Maybe I clicked on a button on a graphical GUI on a web server. Well, it's going to create these JSON strings and the REST request strings and parse the JSON output. It's just very easy for machines to parse that, and humans can read it as well. And the rest is really just the details of what it looks like, blown up a little bit more. And that's pretty much it. That's really all I wanted to talk about on the protocols. Just discussing the fact that there's two sides of it. There's a web server in the middle. The human side is going to interface with the web server through those URLs, or you can go back to the other side. If I go back to the architecture picture again. There. That's really it in a nutshell. You've got IP reachability here. Before, I think last year, I didn't have any of this stuff working. So everything that you wanted to do, you had to have your requester and your responder both being on the XB network, both using handheld remote controls or an infrared to XB gateway. But everyone wants to be able to use their phone, or a lot of people want to be able to use their phone and visually manage your audio system, your audio video system. To do that, really, you have to have a web server, you have to have TCP/IP, and so that was my answer on how to extend the network. You've got local remote management with RF, and now you can go across a routed network, you can go onto your local network, but you have multiple paths. The answer is yes, I can do it locally, I can do it remotely, I can script it, I can have phones, I can have GUI applications manage it. You choose. The whole point about the DIY remote control project is that there isn't really one answer. People have different styles. Some people like rotary encoders, some people like motorized pots, some people like up-down buttons, some people like to press on glass. Personally, I don't like that, so I have a remote control with real tactile buttons. Some people like the LCD display, some people like fluorescent, some people like the LED display. All of this is possible and it all fits within the framework. It's an architecture that is reasonably independent of the kinds of input, output, the control technology you use, and more add-ons or methods of access can be added in. If there's something that comes along later on, we can either have a gateway that goes from that format onto the web server or a gateway from that thing onto the network. There's lots of ways in and out. So let's see, did I cover everything? I think I did. Yep. So just some links. 10-page discussion on AMB's forum. You can take a picture of that, or you can just go to AMB's forum and just search for the PGA thread. You can look at my Flickr site for lots and lots of photos on this. Here's my email address if you need to get to me. De-spam it, of course, remove the X's. And for people who want to build this, I've got some spare boards. If you're able to solder surface mount stuff, if you want to be able to play with the Arduino, learn the IDE, learn a little bit about C programming, a little bit about Python programming, I'm going to be starting a discussion thread on DIY audio, trying to get enough beta testers together. Once we figure out who's going to be on and how it runs, let it soak for a bit, let it run, let's see if we have any problems, and after that, finally I'll just stock the boards. Maybe even get some boards pre-made, because honestly it's about 8 hours of soldering to do this board. It's misleading. It's a 4-inch board, but there's a lot of stuff on it. So if I can get the boards solder baked, then that'll make things a lot easier. And to me, really, the fun was more in the software anyway. The hardware, it was interesting. Building the hardware was fun, but once the hardware is built, you can spend a lot more time customizing the software, adding features, changing how it feels, having side effects. If you do something here, maybe something else changes. One of the modifications I'm working on now is to group a bunch of boxes together. So the boxes right now are 2-channel. What if you have 4-channel or 6-channel, or what if you have an active crossover? So you want to be able to change the volume between them and then keep that offset constant. So as you move the volume, maybe the subwoofer is a little bit lower, and there's a certain ratio. Or even, a friend of mine wants to have a loudness control, so that as you change the main volume, the bass might change a little bit non-linearly with it. You can do that. It's just software. It's just a software trick. So if you gang 2 of these boxes together with the XB radios, you define one of them to be a slave, you set its bass volume, one of them to be the master, you turn the master, and then they'll both move up and down. And the same thing with the web. You can get to them both over the web, you can gang them together. So you could do multi-channel, you could do 5.1, you could do active crossover stuff. That's one of the next things I'm going to work on, is ganging them together and having that work well together. So that's about all I plan to say. I can entertain questions about the software, the hardware, the protocol. Yeah?
Tell me if you have either a target or guesstimate of what a populated board might cost.
Yep. So in terms of the cost, let me get to a board photo. The boards themselves are very, very inexpensive. I went through China for those. They're like $2 a piece for the boards. The parts themselves, let's just go through a quick rundown. The PGA chip, about $10. The op amps, an OPA 2135, I don't know, a couple of dollars. Any 5534, $1 or so. The headphone amp chip here, TPA 6120, I think it's about $10. It's not too much. The Arduino chip, that's like $3. The crystal resonator, 50 cents. What else? Serial port expander, a couple of bucks. $50 or $60. $50 or $60 for everything. The chassis I just built out of plastic, that was maybe $15 worth of laser cut plastic. Power supply, transformers, about $20. Those toroids are expensive. LM 7905, 7805, $1 or $2 a piece. $100 or less for the entire thing. And that's using All prime parts, all Mauser, all DigiKey. If you cut corners and you went through eBay, maybe half of that. I don't personally recommend it, and I do recommend that you get all the key chips from a real supplier, because there are known to be fakes of the PGA chip and the op amps as well. And it might work, but it might not work as well. Oh, what else for cost? The XB cost, forgot to mention that, that's $20. The rotary encoder is $15 through eBay or through Amazon. The LED display, that's about $10 from Adafruit. I'm currently looking at another source for that, but it's an entire 4-digit LED module that you can get in red, yellow, green, or blue. You can't change the color dynamically, but you can change the brightness. And it comes in either pure 7-segment numeric or 14-segment alphanumeric. So you can actually, if you wanted to, you could have your port name show up. You could have 4 characters, you could glue a second one to get 8 characters, and you could spell out a reasonable amount of activity, messages, whatever. Even time of day, you could have a calendar built into that. Any other cost issues? That's about all I can think of. Not very expensive. Sorry?
Chassis.
Oh, chassis. The chassis I built myself just at Tech Shop with a laser cutter. The time can't really account for that, but cost $15 for a sheet of plastic. Now note that metal would be better, but I've actually gotten pretty good response in terms of hum and noise just sitting in the plastic box. The PC board, Jeff did a great job laying it out. Again, really good thanks to Jeff Wilhelm. He did an amazing job. He followed all the right analog rules, and we've got enough analog and digital ground plane joined by some ferrite beads at the right point. It's fairly low noise, and even sitting on top of something that has a trafo, it's not picking up hum. So layout was key, and ground planes were key. Yeah?
Is there any kind of like node ID within the system? I'm just thinking if you want to like pull power or something for each individual device.
Right. Currently, I don't have support for naming the boxes or giving them addresses. I do plan to, because you might have several instances of that box. You might have a preamp upstairs and downstairs. You don't want them responding to the same address. I've hesitated adding more to the protocol until I feel comfortable enough with the response time right now. If we add node IDs, we have to add a bunch of stuff. We have to have the source ID, the destination ID, maybe a protocol type, the way Ethernet kind of is. That adds more to the payload. That means more characters have to be sent across, and then when you do back-to-back messages, it's going to be slower. There are ways around it. Instead of having to address individual boxes, you can use addressing in terms of namespaces. VC1, VC2, VC3. This is this volume control, that's that volume control. That might work, and that gets you around the entire source and destination addressing things. But I do actually want to name the box. I want to give it some comment fields. You can give it a name, a location, hardware revision, software revision. There's going to be some diagnostics on there, temperature, voltages, health of the box. I want to be able to query the box. Ideally, I want to query a network, discover all the boxes, and then automatically place them on the map based on where they are. So if you configure this box and you say its location is upstairs in the bedroom, and this box is downstairs in the den, you store those strings in EEPROM. When I connect to the box and I discover all the boxes, I say, where are you? What are you? I'm a PGA, I'm version 2.2, I'm a blue board, and I'm located downstairs. That's information you don't get from Sony's and other kinds of off-the-shelf equipment. Here you can add this value-add management, and they're just comment fields, but they can be really useful. Yeah?
Will you provide any libraries for this, or sort of example implementations that can be studied?
Definitely. Python web server is more of an example than something production. Python is inherently source code based, so when I release that, you'll be able to get the code and play with it. And there's definitely going to be an API as well. So an API at different levels, an API to change parameters within the box at the Arduino level, an API to be able to read and write things across XB, an API which is the REST API. API. That essentially is your public API to get to things without worrying about, do I go through IR or XB or Bluetooth? You just connect to the web server. So definitely, it'll be fully documented. It's still in the process of changing, so I really can't release an API because it's still research and development. But once it gets to a steady state, absolutely, it'll be fully documented. You'll get all the source code, PC board layout, schematic BOM, the whole thing. Any other questions?
At this time,
Okay.
I think I want to have everybody thank Bryan